The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is Drew Burns and I'm the Executive Director for the Slag Cement Association. I'd like to welcome you to today's webinar, Mitigating Alkali Silica Reaction in Concrete with Slag Cement. We are glad you could join us. Attendees are in listen-only mode. You may ask questions using the dialog box in the GoToWebinar software. Our speaker will be happy to address questions at the end of the presentation. The ideas expressed in the following presentation are those of the speakers and do not necessarily reflect the views of the Slag Cement Association or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your slag cement professionals for assistance. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. The description for today's webinar is shown on the screen and also listed on the SCA website with the webinar series information. Now I'd like to introduce our speakers today. Keith Maddrey is a technical services engineer with Argos, USA. He received his BS in Civil Engineering from Old Dominion University, Norfolk, Virginia. He worked for the ready-mix concrete industry as a technical services manager for 26 years prior to coming to Argos in January of 2020. Maddrey is an NRMCA Level 4 concrete technologist. Clayton McCabe is also a technical services engineer with Argos, USA. McCabe received his BS in chemical engineering from Carnegie Mellon University. He worked for the Cement and Concrete Reference Laboratory at the National Institute of Standards and Technology as a laboratory inspector for 6 years before beginning work as a technical services engineer in 2007. And now I'll hand things off to Keith and Clayton to get started. Thank you.
Great. Well, thank you, Drew. I really appreciate the opportunity to be here presenting on, I think, this incredibly important subject in our industry. And I'd like to welcome everyone. I hope everyone's healthy and families are as well, and you're navigating this craziness that is 2020 as well as can be expected. And so I will mention up front that with as many folks as we've got in the meeting, there's probably going to be different levels of exposure to this subject prior to this. So my hope is that everyone would come away with at least another tool for the toolbox. And if the information is not brand new to you, that at the very least, maybe you get some clarification or reinforcement of a question you may have had previously. So for the presentation overview, Clay and I are going to be splitting this up. So for the first several slides, I'll be talking about slag cement, properties and benefits, and overview how it works in a concrete system. Clay is going to take it over from there and do a lot of the heavy lifting, and he'll talk about a definition of ASR, the mechanisms that are involved in that, and then most importantly, what do we do about it? How do we prevent it? How do we work on the front end to mitigate ASR, and specifically using slag cement to combat it? He'll also talk about testing methods that are involved in the process. And then lastly, I'll be showing you a few case studies where slag cement has either been used or is in use on particular projects. So, next slide. So the question is, what is slag cement? And it is a white powder that's used as an SCM or supplementary cementitious material. And the goal is to enhance the properties of the concrete. In the presence of moisture, slag cement will exhibit hydraulic properties similar to Portland cement. So if you mix slag cement with water, it will set up, it will gain strength. And so where does it come from? You need an iron ore blast furnace. And so typically prior to production of steel, some other metals, You have your molten iron ore, and then you have your non-metallic molten material, which is the slag. So in this process, the slag is diverted from this waste stream. And once it is, it's rapidly quenched and then cooled. And once this happens, basically what is produced is a glassy granulated product. That's not the end of the process. Next slide, please. So once that happens, these granules are ground to a suitable fineness. And so your question might be, what is a suitable fineness? And it's typically finer than Portland cement. And to give you an idea of that, a pound of Portland cement can have 150 billion grains. So incredibly fine. Once this finished product is produced, it's used in concrete mixtures to enhance durability and sustainability. And if you're looking at the pictures from left to right, there on the left obviously are the slag granules themselves after the cooling process. The picture in the center is a microscopic view of slag cement, and this is the finished product after grinding. And the picture on the right is obviously a slag cement grinding facility. Next slide. So a lot of things going on in this slide. We're talking here about slag cement reaction. So there's two concrete systems represented here. On the left, you've got a Portland cement concrete system. On the right, you've got a Portland and slag cement concrete system. And as you're looking at this, the gray is going to represent your cement particles. The yellowish tannish material is calcium silicate hydrate. Now this CSH is the primary product from Portland cement and water hydration. It's also the glue, kind of responsible for the strength. The white areas in between are voids, and there is some calcium hydroxide or free lime in those areas. On the right, as you're looking at the Portland slag cement concrete system, you'll notice that there's fewer hydrated cement particles. There's fewer voids. There is more of the CSH present. And there's a couple different benefits that you're getting from the slag in this situation. One is physical and the other is chemical. So from a physical standpoint, you've got your particle size distribution, the shape of the particles, that sort of thing. And so you are getting some particle packing, which is going to help to densify the product. Second, you are getting some benefit from reaction of the slag with the calcium hydroxide to produce more CSH. So in this particular case, more of the calcium silicate hydrate. And as you look at the illustration, what you can see very clearly is you end up with a denser product and a reduction in permeability. And anytime you have a reduction in permeability, you're going to get a more durable product. Next slide. So just a summary of slag and the properties and attributes. You're getting similar reactivity to ordinary Portland cement. There are differences in phases and mineralogy, but the reaction itself is similar. Typically, the replacement level of slag cement to Portland cement is going to be 1-to-1. So if you hear us talk about a 50% slag mix, it's literally 50% of the Portland cement pulled out, replaced by 50% slag cement. Is a hydraulic cement, so again, in the presence of moisture, it will hydrate. You will get strength gain and set. Produces a stronger concrete, so it's denser, less permeable paste, again, attributes to durability. Better slump retention, easier placing, consolidation, and finishing. Typically with the slag cement mix, you're going to see lower early strengths than you are with an ordinary Portland cement, but at least equal higher 28-day compressive strengths typically. Several variables involved in that process, but generally speaking, slag is going to perform better down the line, even extending this to 56 days or possibly even 90 days, depending on replacement levels. You also get the benefit of lighter colored concrete, so it's providing reflectivity. I've had jobs in the past that were small residential jobs where customers might even want a slag mix for, say, a pool deck because they wanted a, almost a bright white concrete. And without the expense of a white Portland cement, slag can give you a lighter colored concrete. This also provides some benefit from reflectivity and UHI, and UHI being urban heat index effect. So basically, if you've got darker colored building materials, let's say you've got asphalt, different things like that, obviously that's absorbing heat and that's dissipating into the surrounding air. And obviously, if you have reflectivity, lighter colored concrete, that is being reflected. And so there's some advantages there. Enhanced durability is a big one. So again, anytime you talk about reduced permeability, you're getting a more durable, sustainable product. It's also more sulfate resistant than ordinary Portland cement-based concretes. And so there's a tremendous amount of benefit that comes with adding slag cement to your mix. And I'm going to turn it over to Clay at this point.
All right, thank you, Keith. So next we'll talk about ASR specifically. So what is alkali silica reaction, ASR? It's the chemical reaction between the alkalis in concrete, usually from the Portland cement, and certain types of silica reactive minerals that are in the aggregates. So the alkalis are reacting with the aggregates. And this reaction produces a hygroscopic gel that absorbs moisture and swells. And this swelling can cause expansion and eventually cracking in concrete. And you can see an example there in the picture, and that's obviously something we do not want in our concrete. Next slide, please. Okay, so the factors that affect the rate and severity of ASR. Number one, I think the biggest factor is the reactivity of the aggregate. You can have different aggregates have different reactivity amounts. So that's the biggest factor when looking at ASR is the reactivity of the aggregate. Also, you want to look at the availability of alkalis in the concrete. Again, for the most part, you're looking at the Portland cement. But there also might be external sources of alkalis. That might be from de-icing salts or from ocean waters. You also want to look at the exposure conditions. That's the moisture availability and the temperature, and also the type of concrete element, its size and reinforcement. You can also see there the note at the bottom that ASR damage can work in concert with other types of damage. If you've got ASR damage to concrete, that might promote other types of damage, such as freeze thaw or corrosion, and the vice versa is also true. If you've got freeze thaw damage to concrete, and you've got cracks starting to form, that will accelerate any type of ASR damage. Next slide, please. Okay, so how does slag mitigate ASR? The following is from ACI 233R, and I first want to note that the effectiveness of slag cement in mitigating ASR was first reported in 1950. So this is something that's been known for a long time, that the use of slag can help mitigate ASR. Next, we've got listed 5 factors of how slag helps to reduce ASR damage. The first one is the reduced permeability. Again, I think that's a big factor with the durability benefits of all different types of attack associated with the use of slag. As Keith showed in the one diagram, the reduced permeability in systems containing both Portland and slag. You've got the smaller and less interconnected void structure leads to the reduced permeability that really helps with durability all around in concrete containing slag. The next 3 factors listed there have to do with alkali contents, both in the direct reduction of available alkalis in a concrete system, as well as a reduction in the alkali silica ratio in the concrete, and also the actual hydration of the slag itself consumes some of the alkalis. So when you've got slag in your system, it helps reduce the available alkalis that might contribute to ASR damage. And the last factor listed is a reduction in the calcium hydroxide, and the calcium hydroxide is kind of a support the ASR reaction, so it's helpful to reduce the calcium hydroxide. And that's also a big part of the reduced permeability, is the reduced calcium hydroxide associated with systems with both Portland cement and slag. Next slide, please. Here we've got a graph showing just how important slag can be in mitigating ASR. What's shown is C1293 test results with 4 different reactive aggregates. We can see the tall gray bar being the all Portland cement mix, and then we've got increasing slag amounts of 25% up to 65%, and you can see the expansion due to ASR, how that reduces as we increase the slag replacement levels, from high expansion at 100% Portland cement down to very, very small amounts, especially when we get up to 50 and 65% slag. Very, very little expansion. This is really showing the effectiveness of slag and mitigating ASR. All right, next slide, please. Okay, so we know now what the ASR is, and we know we don't want it. So what do we need to do about it? Once ASR begins, it's very difficult to stop it. You could try and stop it by eliminating water getting into the system, but it still can be very difficult. So really the most effective way for mitigating ASR is preventing it in the first place. So the prevention involves looking at the proper materials needed in the concrete mix design when the concrete's first being placed. And then you can see 3 factors that we want to look at as far as limiting the alkali content in the concrete, limiting or prohibiting reactive aggregates, and specifying slag cement to prevent ASR. And now all 3 of those are encompassed into the guidance, into the documents ASTM C1778 and AASHTO R80. Those documents give comprehensive guidance on mitigating ASR, and those will be the next dozen slides I will go over will be regarding the guidance in those 2 documents. But before we get there, I did want to note with regard to limiting the alkali content in concrete, I wanted to note that while Portland cement alkalis can lead to ASR, they also have positive impacts on concrete. Portland cement alkalis can also help protect rebar and prevent corrosion damage. They help promote hydration and strength gain, especially in mixes containing SCMs such as slag. And they also can improve the effectiveness of some admixtures. So just wanted to note that there are some positives and negatives to Portland cement alkalis in concrete. All right, next slide, please, Drew. Okay, ASTM 1770 and AASHTO R80. These are 2 documents that provide comprehensive guidance on ASR mitigation. AASHTO R80 started as PP65. It was a provisional standard that was adopted by AASHTO in 2010. It's now a full standard as a R80. I believe the current version has a 2017 date. Similarly, ASTM C1778 was adopted by ASTM in 2014. These 2 documents are very, very similar and provide very, very similar recommendations. Many state DOTs have incorporated these approaches, this guidance, into their state specifications regarding ASR. Pennsylvania, Maryland, Texas, and West Virginia all have ASR specifications that are similar to these documents, especially Pennsylvania, and the what's being proposed for West Virginia, just a draft spec at the time, but looks like it'll be very similar to the guidance provided in these specifications. And these specifications provide 2 performance options and 3 prescriptive options of how one would go about mitigating ASR. And I want to note here that all of these options can utilize Slag to help mitigate ASR. All right, next slide, please, Drew. All right, so the first step in both of these documents is to classify the aggregates. Now, both documents have similar flow charts of how you classify the aggregates. They've got solid lines as the preferred method and dotted lines as an alternative method, though with increased risk associated with those. And these steps involve, looking at field history and testing. Also, they might involve, looking at the petrography of the aggregates. And 2 of the biggest test methods that they're looking at is ASTM 1260 and ASTM C1293. C1260, or the accelerated mortar bar test, is a 16-day test. The bars are in solution for 14 days, but the 1293 test is a year-long test. That's the preferred test, but obviously it takes much longer to get your result with a year, though it provides recognized as a more accurate result. So again, the 1293 is the preferred test, but the 1260 being the alternative. So, in the result of this classification of the aggregates, we've got 3 possible outcomes. The first being the aggregates are non-reactive. Oh, that's great. We can stop worrying about ASR in this particular concrete. If your aggregates are non-reactive, you don't need to pay attention to ASR any further. The second possible outcome is if the aggregates are alkali carbonate reactive, not alkali silica reactive, but alkali carbonate reactive. In this case, it's not recommended to use these aggregates in concrete. The third option is that the aggregates are alkali silica reactive, and in this case, you want to take preventative measures, and that's what the rest of the documents will be about, is how exactly to properly mitigate these particular aggregates. All right, next slide, please. Okay, we said there's 2 possible performance approaches. The first one being the C1293 test, the second being the C1567 test. And both of these, approaches use a testing procedure to evaluate if a particular aggregate can be properly mitigated with a certain SCM replacement level. In this case, slag cement. So you'll test your aggregate with a particular slag usually with different replacement levels for both of these tests, and find a replacement level that properly mitigates ASR. Again, the 1293 test, this time we're going to 2 years, not even just 1 year, but looking for a 2-year result. And similar to C1260, the 1567 is a 16-day test. So if the 1293 2-year result is not greater than 0.04%, then your slag replacement level has been shown to properly mitigate for ASR. Similarly with C1567, if your test result is not greater than 0.1%, then the SCM, the slag replacement level, has been shown to properly mitigate for ASR. One caveat with the C1567 test, you can see in the lower right, there's a chart, and that chart's comparing the C1293 result with the C1260 result. And if these 2 results line up in that zone 3 and with the diagonal markings, then it's not recommended to use the 1567 test. All right, next slide, please. Okay, now from the performance approach onto the prescriptive approach. The first step will be to determine the level of prevention needed, and the level starts with level V, and that's the lowest level up to the highest level of level double Z. And then there's 2 or 3 options for prescriptive approach. The first being the alkali loading. The second option being using a prescriptive SCM replacement amount. And the third option is just a combination of the first 2 options. So you're both looking at alkali loading as well as a set amount of SCM, in this case Slag. All right, next slide, please. All right, and the first step of determining your level of prevention needed, we're back to our C1293 and 1260 results. But in this time, instead of just seeing if the aggregate is reactive or not, we're putting it into a classification. You can see on the left-hand column is the aggregate reactivity class. Your R0 is your non-reactive, up until R3, which is the very highly reactive. And again, we've got the 1-year 1293 test and the 14-day or 16-day total C1260 test. Now, if you've got 1260 results and 1293 results, it's the 1-year C1293 concrete prism test that would override the 1260 test. You'd want to use that 1-year CPT test. So for example, if you've got a C1293 result of 0.07% at 1 year, that places you at an R1 aggregate reactivity class, which would be moderately reactive. Be important to know here that you want to look at both your fine aggregate and your coarse aggregate or aggregates. If you've got, say, for example, an R0 fine aggregate and an R1 coarse aggregate, you'd want to use whichever aggregate has the higher reactivity class and mitigate to that level. So in that case, you'd want to mitigate to the R1 aggregate reactivity class. Next slide, please. All right, the next step is determine the level of ASR risk. And from that, we start with the aggregate reactivity class that we just obtained and compare that to the size and exposure conditions. Aside from the R0, which is level 1 for each of the size and exposure conditions, you can see that the level of ASR risk increases as we go down the list, and increases from the top left corner to the bottom right, from a level 1 to a level 6. So you can see that the lowest level being associated with a non-massive concrete in a dry environment. We've got very low risk of ASR there, where we increase the risk that we now have a massive element in a dry environment. Increase the level further if we've got the concrete now exposed to moisture, and increase the level even further if the concrete's exposed to alkalis in service. And again, those alkalis in service may come from de-icing salts or from ocean water. Next slide, please. Okay, now our next step is the structure classification. And this classification comes from the consequences of ASR and the acceptability of ASR, and goes from an S1 to an S4 class, with an S1 being that some deterioration may be tolerated, up to an S4 where ASR cannot be tolerated. And say that the documents give different examples for each class. For example, an S1 might be a temporary structure. In S2, you'd be looking at your sidewalks, curbs, and gutters. An S3 would be, pavements and rural bridges. Up to an S4, again, the most severe classification being your major bridges and tunnels, where you're expecting a service life over 75 years, 100-year service life. So your most severe structures. All right, next slide, please. All right, so this is where we get our level of prevention that I talked about. We've done all this to get this level of prevention. So we take the level of risk that we previously found and compared that to the classification of the structure to get this level of prevention. And this level of prevention, which is what will guide our level of mitigation that we'll see in the rest of the prescriptive options. So for example, if we have an S2 structure and a risk level 4, that takes us to level X, level of prevention. All right, next slide, please. Now again, the first option for prescriptive option for mitigating ASR is our alkali loading. There we can see with the different prevention levels, we've got different maximum alkali loading of concrete with the prevention level V of having no limit, with prevention level W of being 5 pounds per cubic yard of alkalis, down to prevention level Y of being a maximum of 3 pounds per cubic yard of alkalis. And we'll look at Z and double Z a little bit later. All right, next slide, please. All right, so how do we calculate the alkali loading? It's a simple calculation. You multiply the Portland cement content of your mix times the Portland cement alkali content divided by 100. So for example, if we've got a concrete that contains 600 pounds per cubic yard of Portland cement and the equivalent alkalis, and that's the sodium and potassium, a combination of the sodium and potassium of your cement, of your Portland cement, if that level is 0.8%, just multiply the 600 times 0.8 divided by 100, gives you 4.8 pounds per cubic yard. And if you compare that to the previous slide, that puts you at the prevention level W, since we have not exceeded 5 pounds per cubic yard. Now for example 2, we'll take the same 600 pounds total cementitious, the same 0.8% alkalis in our Portland cement, but this time we'll use 40% slag replacement. So that's 360 pounds per cubic yard of Portland and 240 pounds per cubic yard of slag. So again, the calculation is 360 times 0.8 divided by 100 equals 2.9 pounds per cubic yard. 2.9, we're less than 3, so that puts us at prevention level Y, which is a very high prevention level. It's a very strong mitigation level, being under 3 pounds per cubic yard of alkalis. One thing to note there is that we are not using the alkali content of the slag cement itself, as we mentioned earlier, that the alkalis are actually consumed by the slag hydration. So the alkalis are not available for ASR mitigation, not nearly as much as the Portland cement alkalis are. So it's only the Portland cement alkalis that are used in this alkali loading calculation. All right, next slide, please, Drew. All right, now this takes us to the second option, which is using an SCM. And again, I suppose you could use fly ash or silica fume also, but we're here to talk about slag today. So we just got listed the slag option for mitigating ASR. So what you'll want to look at is that top table there. Say if we need to meet a prevention level X, so that shows 35% slag replacement. Now that 35%, you take that, you want to compare that chart with the chart below it, that it may need to be altered. That 35% is based off of Portland cement alkali content that is greater than 0.7 and less than 1%. Yeah, that's where you use that 35%. Now you alter that top chart by that bottom chart, depending on the alkali content of your Portland cement. So for example, if you're using a Portland cement with an alkali content of 0.55%, you now reduce the level by 1 prevention level. So you move 1 column to the left. So if you need to mitigate to a level X and you're using that 0.55% alkali Portland cement, you now move one column to the left, so you only need to use 25% slag to mitigate 25% replacement level in your mix. On the other hand, if you're using a higher alkali cement, if the alkali content of your cement is 1.2%, now you move one column to the right or increased one level. So if you need to mitigate to level X and you're using that higher alkali Portland cement, you now need to use 50% slag in order to achieve the proper mitigation. All right, next slide, please. And this takes us to option 3, where you're looking at both alkali loading and using a prescriptive SCM amount. So again, this is only for the recommended for the highest prevention levels, Z and double Z. If you're looking at prevention level Z, for example, it lists the alkali loading of 3 pounds per cubic yard. Excuse me, for level, that's the maximum for level Y, and also the SCM replacement level for level Y. Alternatively, let's say if you're just using the SCM replacement level, you want to use the level Z column. However, for this recommendation, if you're using both, you use both at the level Y recommendation. And that's it on 1778 and R80, and I'll now move to Keith.
Great, thank you, Clay. So I've pulled a few projects here we're going to take a look at, and the first couple come from Drew's library, actually. And so this was an award winner back in 2018, and this was in the category of durability. So this is the Indian Lake Spillway in Russell's Point, Ohio. Next slide, Drew. So this is the second largest labyrinth-style dam in the United States and the largest east of the Mississippi River. Now, if you're anal like me, and that just charges the question, well, what's the first? It's the Ute Dam in Logan, New Mexico. So there you've got a little piece of trivia to go with. Standing over 16 feet high and 700 feet long, and with the storage capacity at principal elevation is 15 billion gallons of water spanning over 5,000 acres. So there was 7,300 yards of mass concrete used on this project. The producer was Ohio Ready Mix. And so the designs they used in this had a 50% slag substitution. And this was for 3 reasons. The first was temperature control for the mass concrete, ASR mitigation, and then also to help reduce shrinkage. So had a very low water cement ratio in this and utilized a high range water reducer. So this was a 4,000 PSI design for 28 days. They were getting average strengths at 7 days with this 50% replacement level of 2,600 PSI, and then more than doubling that at 28 days. So they were well in excess of the 4,000 PSI design strength on this one. Next slide. So aesthetically, you can see it's a pretty cool looking project, very attractive to tourists and people driving by, not only because of the design of the structure, but also, again, lighter concrete and bright white walls. The finishability for this particular one, the contractor said, was great, and the overall design strength well exceeded what the engineers were expecting. So the owner on this one, Ohio Department of Natural Resources, Stantec Engineering, CJ Mahan, Ohio Ready Mix Incorporated, and then the slag cement was supplied by St. Mary's. Okay, next slide. This one was also a 2018 winner, and this is in the category of innovative applications. This is the Meadow Lake Wind Farm in Remington, Indiana. So this was phase 6 of this project and consisted of the construction of 61 wind turbines. And so they chose this obviously as an area with a proven wind resource. And so the project included not only 61 wind turbines, but also transmission lines and a new substation. So all the concrete in this project contained slag in various amounts. And there's about 48,000 cubic yards of concrete in this particular project. Next slide. So they wanted to expedite the process on this job, so the concrete was actually required to obtain 60% of compressive strength in 48 hours for stripping purposes, and still had to meet the 28-day requirement. Some design challenges within that because of the typical a little bit lower early strengths on the slag, but in this case they were able to affect that change within the design structure and hit those requirements. The slag was employed to better control, again, temperature rise of mass concrete for the foundations. So they placed thermocouples into the mass concrete and made sure that no foundation allowed temperatures in excess of 160 degrees Fahrenheit. They also used slag cement at a 30% substitution rate to mitigate alkali silica reaction and to aid with the overall consistency of the concrete that they used on this project. Next slide. So a couple of fun facts. The anticipated output is a little over 200 megawatts with a total capacity of a little over 600, which is enough to power roughly 157,000 average Indiana homes. Obviously, the environmental upside here is tremendous. The project team on this one included EDP Renewables North America, Mortensen Construction, Barr Engineering, Irving Materials Incorporated, and the slag in this particular case was supplied by Lafarge Holcim. Next slide. This one is an actual ongoing project here in my area. I'm in the Norfolk, Virginia Beach area of Virginia, and this is the Hampton Roads Bridge Tunnel expansion. In this project, it connects the cities of Norfolk and Hampton, Virginia. So the picture that you're looking at currently, this is the Norfolk side, the Norfolk waterline there. And then as you can see, there's a two-lane span heading each direction. So there's east and west spans, a total of 4 lanes that connect these two cities. Next slide. So huge project. There's approximately 580,000 cubic yards of concrete in this particular portion of it. And obviously on a project of this size with these kind of structure, there were enormous considerations for what testing had to take place and what it went into deciding on materials and mix designs for this project. So they had to account for mass concrete, temperatures, ASR, shrinkage, permeability, freeze-thaw durability, strength, and chloride ion concentration, and that's just to name a few. Next slide. So as you look at this, these 4 lanes connecting these two cities, just to give you an idea of the traffic impact here, during summer peak hours, they can have as many as 100,000 vehicles in a 24-hour period. And the capacity of those 4 lanes right now is approximately 4,700 cars per hour. So if you do the math, you can see there's really never a time in peak hours where there's not traffic here, and it's quite often you can be caught in 5, 6, 7 miles of traffic leading up to this kind of bottleneck here. So the changes that are proposed are just to the west of these 4 lanes. There's going to be 4 more lanes that are constructed. So now the 4 lanes that are currently in use will become the westbound traffic heading from Norfolk to Hampton, and the new proposed 4 lanes will bring the eastbound traffic from Hampton to Norfolk. In addition, the areas on Interstate 64 leading to the bridge tunnel from either side will be expanded from 4 lanes to 6 lanes with a drivable shoulder. So the analysis basically says that it will expand it from a capacity of 4,700 cars per hour to 6,300. So you can see it'll be a significant reduction in that congestion, hopefully. Next slide, Drew. So to get into a few of the specifics on this one, the ASR specification on this project was a little different than we've seen and what is suggested from even C1778 and R80 as Clay explained them to you. The specification on this one actually requires an expansion of less than 0.08 at 28 days as determined by 1567. So to go back again to what Clay was bringing to you, the 1567 is from the performance-based side of that mitigation process. And so this, the aggregates had to be submitted, to be tested with the reduction level of slag cement that they wanted to use in this. So at the beginning stages, they actually ran ASTM C1260 on the two individual aggregates. And again, remember that the requirement from C1778 says that less than 0.10 or a max of 0.10 at 16 days is enough. This requirement was much more stringent than that. So those 1260 readings from the aggregates initially, the test was modified, taking it out to 28 days, with the readings being 0.17% for the coarse and 0.10% for the fine aggregate, respectively. And so they were both out of the specification. So the decision was made to run the C1567 utilizing a substitution of 50% for the mixed designs. After running that test, they came back with readings of 0.02% for both the coarse and the fine. So as you can see, there was a dramatic reduction in the expansion according to 1567 with the use of the 50% slag cement in this case. Next slide, Drew. So this project is actually a design build and it's slated for completion in November of 2025. The construction team involved with this one is VDOT, the Hampton Roads Connector Partners, which includes several different companies, Dragados, Vinci, Flatiron, and Keller, just to name a few. The concrete producer is Commercial Ready Mix, coarse aggregate producer Vulcan Materials, and Argos USA. We are supplying the type 1-2 cement and the slag cement for this project. And I think that concludes our presentation, Drew.
All right, thank you guys. We do have one question that came in, and the question is, does particle size of slag have any effect on ASR?
Okay. Clay, do you want to take that one?
I would think some, but I would say very little. I mean, everything in concrete is a trade-off. So if you've got a finer particle size, you would get more complete hydration. But on the flip side, if you're letting your water, not adding more, high range, then you would have a higher content of water needed into your mix. So that would kind of be on the opposite side. So that would be hurting your ASR. So overall, I would say that the size of the slag would have a small, very small impact. I wouldn't think would be. It's not something that you really need to account for, and it's not something in the 1778 or R80 guidance.
All right, thank you guys.
I did want to mention.
Go ahead.
I did want to mention one other thing earlier regarding the prescriptive SCM prescriptive slag replacement chart. There is listed a maximum alkali content on the slag cement itself at 1%, and that's not to say that slag's above 1%. contribute more to ASR, and slags under 1% do not. That was more based on that, all the slags, the cements that we found were under 1%. So I guess it's more of a preventative measure in case of contamination or something weird going on. But say it shouldn't be a factor in any designs, but there is that caveat in the replacement level chart of 1% maximum alkalis on slag.
Okay, doesn't look like we have any other questions that have come in. Let me just check and make sure. Oh, yep, we do have some more. Maybe you've already answered this, but the question is, does high alumina 18% plus adversely affect ASR resistance as it potentially does for sulfate resistance?
I wouldn't think it would be as big of a factor for alkali resistance, but we can get back to that one offline.
Yeah, in addition to that, if you have any other technical questions that you would like fielded through SCA and our technical consultant or our technical and marketing committee, feel free to email me directly. My email address is drew.burns@slagcement.org, and you can find all of our contact information on the homepage of Slag Cement's website, slagcement.org. I want to quickly mention that we have one more upcoming webinar in our webinar series, and that's next Thursday at 1 p.m. Trevor Looney, who is one of our 2018 Research Award winners, is going to be presenting some of his research on ultra-high performance concrete mix designs for use in bridge connections and repair. Again, that's next Thursday, the 27th at 1 p.m. And the information for registering for that is on our website. Please visit the SCA website at slagcement.org for more information on this topic. There you'll find almost 30 technical fact sheets, the slag cement product category rules, environmental product declaration, and life cycle assessment calculator, all free to download on the website. Thank you, Clay and Keith, for speaking today. And thank you to everyone for attending today's webinar. If you haven't done so already, check out the other great webinars that we have recorded. They will be uploaded on our website within the next few weeks. Thank you and have a great day.